Hey guys, so in this video we're looking at logarithmic and exponential equations. Let's see, we're going to start with the exponentials, and we have kind of three styles, and so I'll kind of go through the steps as I run into each example. So this first one is like basis property, and this is where if we can write both sides of the equation with a common base, like x to the a equals x to the b, then that means that a equals b, so I can equate the exponents and solve that. So let me show some examples over here. Okay, so for this first one, there's some 3's going on. So if I write it 3 to the 4x equals 3, and I'm going to write this root as a 1/2. And remember, square root x is the same thing as x to the 1/2. So if I rewrite the root as an exponent, then I have 3 to the 4x equals 3 to the 1/2, which means 4x pretty much has to equal 1/2. And then I just have to solve for x. And so rather than dividing by 4, because that would give me a fraction and a fraction, I'm going to think of this as multiplying by 1/4. It just makes it a little bit easier on the right-hand side. So 4's cancel, I got x, and that's going to equal 1/8. This next one is also an example of like bases. So right now I have 9's and 27's, so those are not quite the same, but 9 and 27 can both be written in base 3. So I'm going to say 9 is 3 squared, and then it's just going to be times this stuff, 2. And that's because if you think about, like, if I had, say I had 9 to the x, say I had something a little simpler, 9 would be 3 squared x, and the reason is this would be like being raised to this power, and remember, when we're raising to a power, that means we multiply. So that's why I do this. And then on this side, 3 cubed is 27, and that's going to be multiplied by x minus 5. So then once I have that, then I can dump the bases and set the exponents equal. So I'll go ahead and FOIL as I'm doing that. So it's going to be 6x, 2 times 1 is going to be -2. And over here I have 3x and minus 15. So I'll bring my 3x over, and I'll bring my 2 over at the same time. So over here I got 3x, and those canceled. So over here I have -13, and then dividing by 3, -13/3. So the next form of exponentials are where we use logarithms to solve. So if we can't write it with a common base, what we're going to do is log both sides of the equation, and then from log form we're going to be able to get that exponent out of the exponent spot and down at where we can get at it. And that's step 2 here, where we bring the exponent down in front using that property that says if I have an exponent, I can write it in front of a log, and then that's going to let us get at the x. So let me show you what that will look like with an example. Okay, so here we have 8 to the 4x minus 5 equals 15. And I can't really do much. I need to be able to get to this exponent. And so the way that we get to exponents is we use logs. So that's pretty much what logs are for, is finding exponents. So I am going to log both sides of this thing. And then what that lets me do is bring the exponent down front. And that was step 2 back there. So now I have 4x minus 5 times log 8 equals log 15. From there, I got a couple of things I can do. I think I will divide both sides by log 8. And log 8 is just a number. So then those cancel. And then the next thing I do is add the 5 over. So that's going to go 4x equals log 15 over log 8, and then plus 5. And then this, I don't want to divide by 4 because then I get that complex fraction again. So I'm going to do that same trick where I multiply both sides by 1/4. And then this is going to give me my exact solution. So it'd be 1/4 log 15 over log 8 plus 5. So that would be the exact form of the answer, or at least one of them. And then to put that in a calculator, if you have the kind of like if you have a graphing calculator, you can pretty much just enter that all in. If you have the little scientific one, I'd go log 15 divided by log 8, and enter, and then plus 5, enter, and just divide by 4 or times 0.25, enter. And that should get you, that all goes well, about 1.5756. So exact form, and then 4 places right here. This next example is also one where we're going to log both sides, but this time it's a little bit different because it has a base e. And so the other thing that's different is there's a number in front, so I want to isolate the exponential piece. So we'll get rid of any constants that might be kind of floating around out here. If there's something adding, I just subtract that over, kind of whatever I got to do to get this piece by itself. So that's going to give me e to the 4x minus 5 equals 7. And then since it's e, I want to make sure I use natural log, just because it'll make it a little bit easier later in the problem. So anytime we see a base 10, we'd go with base 10. Anytime we see e, we want to go natural log. And then for anything else, it really doesn't matter. Whichever one you want is fine. So I'm going to bring my exponent down front. So that's going to look like 4x minus 5 times natural log of e equals ln 7. And then natural log of e, remember this is the same thing as log base e of e. And so this is just 1. So ln e is 1 because it says what power did I raise e to get e? 1. So this just drops out and becomes a 1, which makes it a little bit nice. So now we just have this. And then I'm going to add the 5 over. And I'll throw that in parentheses just to kind of separate it and the 5 to show the ln is only of the 7. And then divide both sides by 4. So that would be the exact answer, and then if we put that in a calculator, we'd go ln 7, probably enter, plus 5, enter, divided by 4, enter. And if we do all that, it should come out to, let's see. Oh, actually this one just wanted an exact answer. So I think on the computer it's looking for that form right there, so careful to give it that. So the third form of exponentials is when they're in a quadratic form. And I notice I actually have a typo here. I should have, we kind of go through the steps. So if it is in the form of quadratic, we're going to get it set to 0. We're going to factor it, and I'll show you a little trick with that. And then we're going to solve each of the factors. So very much like solving regular quadratic. And I have the wrong property here. I should have a to the xy. Sometimes that is helpful to write as a to the x. Y. And so I should get that corrected in the notes. So let me show you an example that uses this. So here we have this, and it doesn't look quadratic at the moment, but it is, and it will be after I do a little bit of work on it. So first thing I'm going to do is get it set to 0. So I'm going to go e to the 2x equals, minus 3e to the x minus 10 equals 0. And this e to the 2x, so if I want this to look a little tiny bit more quadratic, I'm going to write it e to the x squared. And that's the same thing, 2 times x, 2x. But what it helps me do is see that right here, there's another one of those, e to the x, and then minus 10 equals 0. So there's this whole e to the x thing going on. It can be a little bit hard to see what to do with that there, so I'm going to suggest we do a substitution just to make it look a little bit easier. It's the same math, but this is just to give it a little bit different view. So I'm going to let y stand in for e to the x because we're a little bit, it's just going to make it look not quite so bad. So I'm going to let this be y minus 3 times this is now y minus 10. And so by doing that substitution, I can make it a bit more clear to myself how it is this is going to factor. So now I can go, what multiplies negative 10 adds to be negative 3, so minus 5 and plus 2. And so I end up with y equals 5 and y equals negative 2. Except that I invented y, so now I have to come back and take what I substituted out and put it back in. So that's going to make e to the x equals 5 and e to the x equals negative 2. So e to the x equals 5, if I write that in, let's actually log both sides. I'm going to do a natural log of both sides, and I think that'll be easier than if I switch it into, you could also just switch it into log form, but I think I'll lose people if I do that. So let me bring this x down front. ln e equals ln 5. And remember, ln e is 1, so x equals ln 5. And if they want an approximation, we just put that in the calculator and get it's about 1.6094. And what I could have done up here is e to the x equals 5. So the e means it's going to be a natural log, because that's base e of 5 equals x. So I could also just switch to exponential form and get the exact same x equals ln 5. So this side, e to the x equals negative 2. If you think of what the graph of e to the x looks like, or just the graph of any exponential, remember they were like this. They were never negative. Negative 2, that would be a line down here. These things are never going to meet, so we cannot have an exponential equal a negative, because remember the domain, well, not the domain, the range on our exponentials was 0 to infinity. So unless there's like a negative out front, it can't equal a negative 2. So that branch doesn't produce a solution. So that would be our only answer. Okay, then we're going to have a couple of versions of log equations to look at. And basically we're going to have one version where every term has a log, so it'll just be like log, 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 log. And then we're going to have another version where we have like log, log, and then equals some number, or maybe just a log equals a number. So that's kind of how we can tell the difference on which way to go. So if we have the kind that has all logs, I want to write both sides of the equation as single logs. And what that does is it's kind of like the common base thing with the exponentials, where I had e to the, x to the a equals x to the b, so a equals b. With this, if I have log a equals log b with base x, then that's only true if a equals b. So that's what we're going to kind of try to do with this, is get them down to a log equals a log, and then we'll dump the logs and then kind of solve what's left. If it's linear, we want to get numbers on one side, x's to the other. If it's quadratic, we want to get it set to 0 and then factor and solve it. And then, just like the last example, this has one little problem, which is we can't take logs of negative numbers. So if we end up with log of a negative like this in our solutions, then we have to throw out that answer. I'll cover the second one when I get to an example that does it. So here's the first one where it is everything has a log. So this side I'm just going to write as a single log. So it'll be log x minus 5, and then equals log 2x. And so since I have log of this equals log of that, I can dump the logs. And then that lets me solve what's left here. So x squared minus 5x equals 2x. And now that's quadratic, and so I want to get everything over to one side. So I'll subtract the 2x. X squared minus 7x equals 0. And then from there I can factor and solve. So this is just a GCF, so I'll pull the x out front. X minus 7 equals 0. And then that means x might be 0 or x might be 7. Looking back up here, and again, if we think of a graph of a log, the graphs are always how I kind of figure out the domain and range on these things. So our log graphs looks like that. We can't put in 0, that was our asymptote, and we can't put in negatives. So if I put 0 in here, I'm trying to take the log of 0, so that is not valid. If I put the 7 in, everything stays greater than 0, so that one's a valid solution. So then the second form is if there's logs in a number, we want to get it written as a single log again with the number on the other side. And then we're going to do the thing where we change to exponential form, where we go b to the number equals the math inside. And then once we do that, we're going to get something we're able to solve. And so it could be linear or quadratic again, and then we still have to check the solutions. But that's how we're going to get out of that log form into something we can get to. Okay, so for this first one, I'm going to isolate the log, which is our first step. So I'll do that by dividing both sides by 6. Looks like a 0. So now I have ln x plus 4 equals 7. And so now exponentiating this one, writing in exponential form, remember there is an invisible e right here. That ln means log base e. So getting this one switched around, it's going to go e to the 7th makes the stuff inside. So e raised to the 7th equals x plus 4. And then from there we're just going to shoot the 4 over. E to the 7th minus 4 equals x. And that would be our exact solution. So this next one, it is already isolated. So this is the step that everyone has a hard time with on the test, but it's this getting to exponential form. So it's 4 to the 2nd makes the stuff inside. So 4 raised to the 2nd equals x plus 6. 4 to the 2nd is 16 equals x plus 6. Subtract the 6 over, and it looks like x equals 10. Number 9, this time we have subtractions, so I'm going to write it as a single log. Remember, our subtraction property is log a minus log b is a over b. So this is going to be x plus 3 over x minus 1 to the first. And then the all-important step, 3 raised to the 1 makes the stuff. So 3 raised to the 1 makes x plus 3, x minus 1. So this one came out as kind of a rational, so I'm going to multiply both sides by this denominator. And that's going to let me bring that up and turn it into something that looks a little more linear. So 3 times x is 3x, 3 times negative 1 is negative 3, and x plus 3. And then we'll do x's to one side because it's linear, so moving the x over, and then I'll add this 3 over here at the same time. So that's going to give me 2x, 3's drop out, x's drop out, equals 6, and it looks like x equals 3. If I put the 3 back in, 3 plus 3 is 6, that stays positive. 3 minus 1 is 2, that stays positive, so all is well. Let's see, so number 10, I have log 4x, x plus 6 equals 2. So I had a plus, so I'm using multiplication, writing it as a single log. And their second step is to change to exponential form. So we're going to go 4 squared equals, let's go ahead and go x squared plus 6x. And then this is 16, so I'll subtract 16 on both sides. And I get 0 equals x squared plus 6x minus 16. And then from there I can factor. So we have what multiplies to negative 16 and adds to be 6. So plus 8 and minus 2. So that's going to give me negative 8 and positive 2. Be very suspicious of negative numbers. They almost never check, and so this would make it negative in both of them, so that one's no good. 2 keeps both positive, so that one's good. And it can work out that they both work. Neither one works or one works. You just have to kind of check them back there and see. Okay, and this last one's basically the same thing, just FOIL instead of distribute. So we have a log 2, x plus 1, x plus 3, addition, so I'm writing as multiply, equals 3. And then we'll do our 2 cubed makes this stuff. So 2 cubed makes x plus 1, x plus 3. So that'll be an 8. That's going to equal x squared. It'll be 3x plus x makes 4x in the middle, and then plus 3. Take the 8 over. You get 0, and then x squared plus 4x minus 5. So now we got it. It was quadratic, so we got it to 0. Now we can do our factor and solve. So it looks like plus 5 and minus 1 would multiply to negative 5 and add to be positive 4. So I get a very suspicious x equals negative 5, which totally doesn't check. And I get x equals 1 for my valid answer. Cool, and that wraps up 4.6.